Welcome to our 7th lecture on parallel programming with OpenMP and MPI. Today's topics are ccNUMA, cache-coherent non-uniform memory architectures, and Wavefront parallelization with OpenMP. Now, I told you in the beginning, in the chapter about computer architecture, that ccNUMA is one of the most important architectural features of modern shared memory nodes. In a ccNUMA system, the whole main memory is transparently accessible by all cores of the system, as it should be since it's a shared memory node. However, this shared memory is physically distributed across multiple so-called locality domains. Now, since it's distributed, it's only natural that the bandwidth and latency by which cores can access the locality domains can vary across the system. Also, there's potential contention. These are the two problems we see from an architectural and a performance point of view with ccNUMA systems. In the top figure, we see the first system, the non-local access problem. In the non-local access means that a core from one locality domain needs memory from a distant locality domain. This is entirely possible, and the system's hardware takes care of that, so there's no programming necessary, no special function calls or anything. The hardware does that entirely transparently. However, the speed by which the access occurs, meaning the latency and the bandwidth, is different from local access. The bandwidth will be lower generally, and the access latency will be higher. Now, this is a situation you don't want. This is the non-locality problem. The second problem is the contention problem, which is denoted here by the green and red line in the left memory. Contention means that multiple agents, multiple sources want to access a local memory, and the local memory can't keep up with the demand. Now, we know in a typical modern multi-core system, memory is never fast enough to keep up with the demand of the cores for data. However, if you're in this situation that somebody from the right locality domain wants to access the left memory and somebody from the left domain also wants to access the left memory, the problem is, of course, aggravated. So this contention problem we get on top of the non-locality and the access problem in ccNUMA systems. So these are situations we like to avoid. What we want to do is make sure that the memory access from all the cores is as local as possible. So any core on any locality domain should access mainly only its local memory. This is the goal we want to keep in mind. So how do we do that? How do we make sure that the memory access is always as local as possible from the point of view of a particular core, and as distributed as possible from the point of view of the memory, so that all the available memory bandwidth is utilized to its full capacity? Before we go into the details, let me first tell you that the placement of memory, so the decision as to where a certain part of the memory goes, is implemented in the operating system in units of operating system pages. The operating system, or OS page, is the memory unit in which the operating system keeps track of the memory. Often this is 4 kilobytes as a standard value, but usually in practice we use larger values like 2 megabytes or even gigabytes. But think of it as something that the memory is kept track of. So this is the unit in which the operating system decides where to put the memory. So first of all, before we explore how we ensure this local and distributed access, let's investigate how much does the non-local access cost. Here we have a very complicated system. It's a 2-socket AMD Naples system with a Zen architecture. It has 2 sockets, denoted here by these gray boxes. Each socket has 4 chips. Each chip has 6 cores. Each core has its own local L1 and L2 caches, and triplets of cores share a common L3 cache. 2 core triplets, so 6 cores, share a memory interface with 2 memory channels. So in this system, where we have 2 sockets, we already have 8 NUMA domains. Now the question is, what happens if we run a memory-intensive code on one of those chips, let's say on the 6 cores of this chip, but put the memory somewhere else? What is the penalty for memory access performance compared to entirely local access? And we can do that, and I will show you in the next slide how this can be done. So in this system, we have 64 possibilities to place the program with 6 threads and the corresponding memory. So in this diagram, in this table here, we denote in the horizontal axis the CPU node from 0 to 7. So that's one of the 8 chips in the system. And on the vertical axis, we have the memory node. So this is where I put on purpose the main memory for the benchmark. The benchmark itself was the so-called stream triad. It's a very popular memory bandwidth measurement benchmark, very simple loop. All right, so let's look at this table, and we see that whenever the CPU node ID and the memory node ID is the same, we have good performance. This is to be expected, because if that happens, it means that the memory access is entirely local. Okay, the program is running on a certain chip, and the memory is also placed in the local memory of this chip. So under these conditions, we have a memory bandwidth of roughly 32 gigabytes per second. And it's of course homogeneous across the whole system, so all those 8 chips are the same. Now, if we put the memory somewhere else and leave the code running where it is, we have non-local access. But there are different levels of non-locality here. The first level of non-locality we encounter if we put the memory in a different domain, but the domain is still on the same socket. So we're using some kind of internal network within the socket. And this happens in one of these 2 light green squares on the left top and bottom right in this table. Now, as soon as we go away from the main diagonal, this means we have non-local access, and we see the performance drops from 32.4 gigabytes per second down to roughly 21 to 22 gigabytes per second. So by going non-local within a socket, we already lose about 1/3 of the main memory bandwidth. The second topology layer in the system is the socket-to-socket layer. So if one program is running on one socket, but the memory is put on the distant socket, this means we have to use the inter-socket network. And obviously, as seen from these measurements, this network is not able to compete in any way with the intra-socket network. So if you do that, our memory bandwidth drops down to 10 to 11 gigabytes per second, so to about 1/3 of the local value. So this is the cost on this system. This is what you lose if you, by some accident or on purpose, force non-local memory access. As a general rule, the more locality domains you have in a system, the higher the penalty for non-local access. How did I do that? How did I run this program and actually force the memory of this benchmark into different locality domains? I mean, it's simple with the affinity of the threads to cores, because we know there's a mechanism in OpenMP that allows us to do that. But what about the memory? Now, I've done this with the so-called NUMA control tool. NUMA control, or NUMA-CTL, is part of standard Linux distributions, usually in the NUMA tools package. NUMA control is used as a wrapper to your application. So you use it in this pattern, NUMA-CTL, whatever options, a.out. And it can influence the way a binary maps its memory pages. NUMA control can actually do more than that, but this is the functionality that we're going to need here. With NUMA-CTL, you can specify that all the memory pages of your application should be mapped to a given predetermined set of NUMA nodes. And the list of nodes you specify here is just the list of locality domains starting from 0. So with membind, you force the pages of this program into specific NUMA domains. If there's not enough space in these NUMA domains and you force it with membind, then the program will run out of memory and will crash. You can prevent that by specifying, instead of membind, just preferred. Preferred means the system will try to use the specified NUMA domains for memory placement, but if there's not enough space available, it will use other domains. And the last interesting option for us here is interleave. With interleave, the binary is forced to map its pages consecutively in a cyclic or round-robin manner across all NUMA domains specified. So whenever a new page is to be mapped by the operating system, it goes to the next NUMA domain. In this way, all the memory of the program will be smeared out across the list of specified NUMA domains. Now here's two examples. In the first example, this is how I actually ran the benchmark that produced the nice colorful table on the previous slide. So there are two loops here, M and C. They both go from 0 to 7. I'm setting the number of OpenMP threads to 6, and then I'm running this a.out binary under the control of numactl as a wrapper with the membind option set to $M, and M goes from 0 to 7. So I'm forcing the placement of the memory pages of my binary into the NUMA domains 0 to 7. The thread placement into the CPU domains, C also going from 0 to 7. This is done not using the OpenMP standard mechanisms, which would be really clumsy and awkward to use here, but by using a special tool, likwid-pin, which you can learn about when looking at the other lectures and videos I've uploaded into our Moodle system. So whatever it does, just let me tell you that it pins the 6 threads of the application into the memory domain denoted by C, and C goes from 0 to 7. So here, this green command line is executed for all 64 possibilities of combining memory domain and CPU domain. Here's an example for using the interleave option. I'm also running a.out again. I'm pinning it in a specific way, so this little bit strange notation means that the threads of the application are spread out across the system as far as possible, and the interleave option 0 to 7 means that whenever a new memory page gets mapped into the system by the operating system kernel, the next NUMA domain out of the 8 that are available is used for that. So the memory is distributed evenly across the domains, no matter which core accessed it. Alright, so this is how we run these benchmarks and how we take control of the placement. However, what is the default without numactl? Imagine you have an OpenMP code that has so many threads that it spans multiple NUMA domains. How do you make sure that every thread will get its memory in its local domain? This question was not answered up to now. And for that, we need something that we call the golden rule of ccNUMA. A memory page gets mapped into the local memory of the processor that touches it first, except that there's not enough local memory available. So this is something that's extremely important. It's observed by all modern operating systems, including Windows, so you can pretty much rely on that. There's one caveat. If I'm talking about touching memory pages, we mean writing to it, not allocating these pages. And this distinction is critical for understanding what's going on in programs that have teams of threads that span multiple NUMA domains. So here's an example. This is a typical piece of code that could appear in any simulation code. We have a malloc call here, allocating a huge big chunk of memory, n times size of double, converting the pointer to double pointer, and then assigning it to some pointer called huge. Now, after what we said in the beginning, you have to understand that once malloc returns, although malloc delivers an address in the main memory, the memory is not mapped here. So after malloc returns, it is not yet known where exactly, at which physical addresses, this big chunk of memory will end up. Now this seems strange because once I got hold of my pointer huge, I can store stuff there. So if there's no memory behind it, how should this work? It works by labeling these not yet mapped pages as not mapped, and whenever somebody wants to write to these pages, we have a so-called page fault. the kernel is called, the operating system kernel is called, and then the kernel looks up into a table of 3 pages and assigns a physical page to the logical address that we just wanted to access. This is how the kernel keeps track of memory. It assigns physical addresses to the logical addresses that the program handles. So what happens then is whenever we write to such a pointer, to such a region in memory, whenever we write to a new page, this page fault mechanism occurs. So here's the initialization loop that initializes the memory to 0. Mapping takes place here. Okay, we start at huge of 0. Of course, huge of 0 was never written to before. So the first thing that happens in this loop is a page fault. And the operating system kernel has to decide where the first 4 kilobyte or 2 megabytes of this huge chunk of logical memory space should go in physical memory. And then after the first item has been written, after the kernel has done its job of placing the page, it returns to the main program, the first item is written, and then starting with huge of 1, huge of 2, huge of 3, all the following items can be written without any problems, without any additional page fault, because the page has now been mapped. The next time a page fault occurs, this is when the next page is touched without being initialized first. And this is the way how this loop plows its way through this memory. You can make an experiment investigating this. You can allocate a couple of gigabytes of memory on your PC and then just initialize it using a loop as shown here. And you will see that if you do the math and if you take into account the bandwidth by which memory can be accessed, the process of initializing a piece of memory with zeros takes much longer than it should actually take, just taking the memory bandwidth into account. And this is because we have all these page faults that accumulate a lot of time. So the first time you access memory, writing to it takes a lot of time. So this is the point in a program where the mapping of physical memory to the logical addresses in your program takes place. Now, of course, it's sufficient to touch a single item to map the entire page. So instead of covering the whole range of items here in this loop, I could have just written I plus equals page size divided by size of double, where page size is the page size in bytes, which I can request from the kernel if I need to. Alright, so this is the golden rule of ccNUMA. Keep in mind that it is the initialization code that we have to look at now in order to determine where an allocated piece of memory actually goes. Now, what is the wisdom from that? How can we use this knowledge to our advantage when coding parallel programs for ccNUMA data locality? So in this example, we have a simple case of explicit initialization. So this could again be an example from an excerpt from a real code. We have a large number of elements, 10 million here. We're allocating 2 arrays A and B using malloc. And you know that it's actually the init code where the mapping of physical to logical memory takes place. In this case, we have a sequential loop here, initializing all elements of A to 0. Later in the program, we have an OpenMP parallel loop where array B is initialized for the first time, so there was no need to initialize it up here as well. And it's initialized by putting A of A into a function, and the function value is then assigned to B of I. So as far as B of I is concerned, what happens is that the team of threads is started in this parallel region. Each thread gets a part of the iteration space, and within this iteration space it touches the corresponding elements of B for the first time. So each thread that touches a page of B of I first will get this page of B of I into its local domain. And as long as the chunks in which the iteration space is cut are big enough per thread, there's no problem. There's no problem at chunk boundaries, for example. So we get a decent placement of B of I into the ccNUMA domains of the system. However, with A of I, we do have a problem here because, as we know, since the initialization of A of I was sequential, all memory pages comprising A of I went into the first NUMA domain because it was thread number 0, the master thread, that executed all the initialization loop. So this is bad. We have an access problem for A of I here. Now, luckily, it's easy to fix. All we have to do is make the initialization loop parallel. In order to do that, we open a parallel region here. We make the initialization loop parallel with the OpenMP4 directive, and later on, we use the values of A of I in another parallel loop as before to initialize B of I. Now you see that it's not quite as simple as it could be. I'm opening the parallel region before the first loop, and I'm letting it run. I'm keeping it open until the end of the second loop. This is the first thing that's not intuitive. And the second thing is that I specifically put a schedule static on the for directive in order to force a consecutive chunk of iterations for each thread. Now these two things have a reason why I did that. The reason for the static schedule is that I do want a reliable assignment of the iteration space chunks to threads. If I couldn't rely on the OpenMP runtime to assign the same chunk to the same thread for every loop, I couldn't rely on proper placement. So I have to be sure that the thread that gets a specific chunk of I in the first loop is the same thread that gets the same chunk down in the second loop. If this is not ensured, then the whole placement thing doesn't make sense. This is how parallel placement works. I'm initializing stuff in parallel. I'm parallelizing loops that actually don't take any significant amount of time. However, later, for access to this data, this parallelization is really critical. Now, the second peculiarity here is that I'm choosing this ongoing parallel region. Now, there could be a performance reason for that. We know that waking up a team of threads multiple times costs time. So it's always a good idea to try and keep a consecutive ongoing parallel region. But the actual reason here is that the only way that OpenMP, when you look into the standard, how OpenMP can guarantee that this assignment of chunks to thread is the same across parallel loops is to have them put them into the same parallel region. Now, in practice, it still works even if you close the team after the first loop and open it again with the second loop, because anything else would be hazardous to the performance of many programs. But as I said, if you adhere to the standard and take what's written there for granted, then you should take care that if NUMA placement is an issue in your program, you should try to keep the parallel region open end to end. All right, so here's a little additional information. The required condition for this parallel placement to work is that the loop schedule of the initialization loop must be the same as in all computational loops. And of course, this also pertains to the length of the loop. If the lengths are different, then there's no guarantee you will get the same assignment of iterations to threads. So the only choice for a loop schedule is static, or maybe static with a rather big chunk size, a chunk size that's much larger than a single page. So just to be sure, you should specify the static schedule explicitly on all NUMA-sensitive loops. Just to be sure, all modern compilers have static as their default schedule, but this is not backed by the standard. You cannot be sure unless you specify it. Of course, if you're forced to use static schedule, this has some impact on possible optimizations. Let's say you have a loop that has load balancing problems. Writing static in front of it just makes it worse probably. So you would rather use something like dynamic or guided, but static is what you have to use if you are NUMA aware. So this means that if you need to use some dynamic scheduling on loops, or for example tasking, where there's no way of telling which thread will execute which chunk of the loop, the problem cannot be solved completely. There's no silver bullet to solving this problem if you need dynamic load balancing. But even if this is the case, it's still a good idea to use parallel first touch to distribute the memory pages throughout the system so that even though you have some non-local access, at least on average, you have parallel access. Now, everything is better than placing it all into the first NUMA domain. So parallel first touch with static scheduling is still a good idea. How about global objects? You may be aware that in C and C++, if you have global arrays, so on the global scope outside of the main function, these global objects are initialized before the main function even starts. Now, this is a problem because this initialization loop is sequential. In C++, you may easily work around that by making the global structure an object of a class. So this object gets initialized using the constructor of the class, and in the constructor you can use parallel code to do this placement in parallel. In C, however, this might not be solvable if there's no choice of not doing it globally. So if the cost of copying the data is amortized later in the program, you might consider copying the data to some properly placed array and then later copying it back. In C++, we have a problem with standard containers. The vector container is arguably the most popular container in high-performance computing because it gives a guarantee that the elements that are stored in the container are consecutive in memory. If we use a vector container for any performance-sensitive data, by default, these elements are initialized sequentially. So we have a NUMA problem. Now, luckily, there's a functionality in the C++ standard called STL allocators that provide a very elegant solution. I'm going to tell you quickly how this works. So you need to write a special class. The name is not important. I'm calling it NUMA-allocator here. This class has to adhere some very strict and specific rules, which you can read up in the C++ standard. What you need, in any case, is an allocate function. And this allocate function is called whenever an object of this container type is instantiated. And within this allocation, you are responsible now for actually getting hold of the memory. You can use malloc for that. And initializing the memory with sensible data. And this initialization can be done in parallel. Of course, there's all sorts of questions here. First and foremost, which schedule should you use for this loop? But this can all be solved. Here's just a basic proof of concept. So here we allocate the memory using malloc. We have a parallel loop, and we make it a little bit more efficient by only touching one element per page by using this trick with a page bits define. And in the end, we have parallel initialization of this memory space, and we return the pointer to the space. Now, once you have this allocator class, you can use it when instantiating a vector container object just by specifying it as a second template argument in the constructor. So you should write to vector double NUMA-allocator double of x 10 million. And this way, when initializing x, the parallelized NUMA-allocator will be used. Of course, if you don't use containers, but arrays of C++ objects, a similar problem occurs when instantiating these objects using their default constructors. And there's also a solution for that. If you want to know more about that, you can read this up in our book. Even though you might have a suspicion that your code is plagued by bad ccNUMA locality, how can you be sure? How do you diagnose bad ccNUMA locality? Now, first of all, bad locality always limits scalability of the code. So whenever a NUMA domain boundary is crossed, you run on one NUMA domain, and then you run on two NUMA domains, and it doesn't scale. Of course, that's just an indication, because you know from the beginning, from the first lectures, that there are many reasons why a code doesn't scale, possibly. So there could be Amdahl's law, load imbalance, communication overhead, many different reasons. So the code not being scalable is just an indication, but not a proof that we have a NUMA problem. However, the signature is quite distinctive. So here we have a performance graph of some code, memory-bound code, on a machine with two 8-core NUMA domains, so 16 cores per node, and the NUMA domain boundary is beyond 8 cores here. From 1 to 8 cores, we have the typical performance pattern of a memory-bound code. And then beyond 8 cores, it doesn't get faster, a little bit, but not much. And eventually it even drops. So this is a typical signature of a NUMA problem, this particular shape of the scaling curve. However, it's still not a proof. You can make a test if you run your code with NUMA-ctl --interleave as a wrapper, and then your code gets faster. That's another hint that NUMA is a problem. Why? Because if you interleave the pages across the system and it gets faster, it means that this additional parallelism in the access to the memory pages, even though you have non-local access statistically, but the additional parallelism gives you more performance. So this means initially there was not enough parallelism in data access. So this is a simple test. If you have a very strong, severe NUMA problem, then NUMA-ctl --interleave might unveil it. Keep in mind, however, this is all only relevant if the code is actually sensitive to memory access. It doesn't have to be strictly memory bound, but it has to have a significant memory bandwidth utilization. If the code is entirely core bound, like the ray tracer or divide benchmarks that we used in the exercises, then you will not sense any NUMA problems, of course. There's also a way to directly measure the impact of NUMA non-local access using so-called performance counters. Now that's an advanced topic that we're going to touch upon from time to time. There's tools for that, for example, likwid-perfet counter, and I also put a video about likwid-perfet counter on the Moodle page to let you know about that. Now, with likwid-perfet counter, you can run your code and instruct the system to count certain events that occur while your code is running. And you can configure it to listen to the system and listen to specific events. In this particular case, on this particular system, we listen to NUMA events. So when did a remote NUMA domain request some data from the local domain? This can be counted. There are sensors on the chip that can sense this kind of condition and count when it occurs. And in this case, if we look at the red numbers, we have 3 red numbers: local DRAM bandwidth, which is just the local memory bandwidth of the NUMA domain, which is initiated by actually local accesses, and remote DRAM bandwidth, which is also the bandwidth of the local NUMA domain, but as initiated by distant cores in other NUMA domains. So this data means that about half of the overall memory traffic of this NUMA domain is caused by the remote domain. And this is a proof, that's actual proof, that this code has a NUMA problem. All right? Unfortunately, not all systems actually support counting NUMA events. You have to be lucky. And sometimes the NUMA events are good, like on this system. Sometimes they're only qualitative, so the counts are wrong, but at least the ratios give you some information. And on other systems, you don't even have the option of counting NUMA events. That's very sad, but this is just expressing the fact that this kind of counting facilities is not a high priority with CPU vendors. Now, to wrap this up, I'm going to show you a little experiment, also running stream triad again, so a very strongly memory-bound benchmark in 3 different ways on this complicated AMD system that we showed before. So we have 6 cores per locality domain and 8 locality domains overall. We run this code with 6 cores, 12, 18 cores, and so on, on different numbers of locality domains, doing different placement strategies. The green bars show perfect parallel placement using NUMA-aware parallel first touch. So this is how it should be done. And we see that as we increase the number of locality domains, the performance rises linearly up to 8 domains. So this system is scalable from a NUMA access point of view. The hardware can do it. If we use LD0 placement, so here in this case I forced the placement into the first NUMA domain using NUMA-ctl -m0, then we see what happens. There's no difference on one domain, of course, because there's no non-local access possibility. But as soon as we cross the NUMA domain boundary, performance goes down. It goes down to about 60% of the single domain value with 8 domains. So this is bad. Everyone fights for this memory bandwidth on the first domain. That's one problem. But also everyone fights for bandwidth on the interdomain network, which is even worse. The interleaved placement on this system is actually not so bad. When going from 1 to 4, we have some decent scalability. It's not as good as perfect parallel placement, but you see the difference between doing it entirely wrong, LD0, and doing it in an interleaved way. So this is what I meant with try it with NUMA control interleave. If your program gets faster, you have a NUMA problem. You also see that as soon as the number of NUMA domains gets really large, the penalty from this random non-local access also gets large. So even though we're much faster than the LD0 case, it's still more than a factor of 2 slower than what it could be if we did everything right. Again, keep in mind, these NUMA effects are stronger if we have more NUMA domains in a system. But if you observe the development, the evolution of a high-performance computing system over the next couple of years, you will see that the number of NUMA domains tends to get larger. So this is something you need to be aware of. I'd like to finish with a weird observation and something to keep in mind when looking at modern systems in ccNUMA. So here we've done an experiment. I ran a memory-bound Jacobi solver with sequential, so non-NUMA-aware data initialization. Jacobi solver is a memory-bound code. Let's not discuss what it actually does. It is well parallelized, so there's no Amdahl's law or communication problem, but I've deliberately omitted any parallel data placement. So this initialization of all the memory in the program is sequential. So I expect no scaling across locality domains. This program has a parameter, a convergence threshold, which of course determines the runtime, because iterative algorithm, the tighter the convergence threshold, the longer runtime. So here in this experiment, I'm doing 4 runs. Convergence threshold data goes from 10 to the minus 8 to 10 to the minus 11. And of course, the smaller it is, the longer we need to get convergence. So it's like an indirect way to determine the runtime of the program. Now, the observation is that if the convergence threshold is loose, like 10 to the minus 8, we have the expected behavior. Here we see performance versus number of locality domains. From 1 to 4, performance drops. So this is the typical behavior we expect from a non-NUMA-aware program. And the parallel efficiency is actually 0.18 at 4 NUMA domains, so really bad. However, as we increase the runtime, or as we tighten the convergence threshold, the runtime gets longer and longer, and the longer the program runs, the better it scales. So at delta equals 10 to the minus 11, where the runtime is about 90 seconds instead of 0.5 seconds in the beginning, we get almost perfect scalability of 0.96. So the convergence threshold data in some way determines the runtime, and indirectly seems to determine or seems to have some impact on the NUMA awareness of this program, even though I didn't put in any NUMA awareness from the start. I didn't use parallel initialization at all. So what happens here? Something seems to heal the bad access locality on a time scale of tens of seconds. It doesn't work if the runtime is just half a second or 2 seconds. But it does work if the runtime is 1 minute or 5 minutes or more. So what happens here? The solution to the riddle is NUMA balancing. The Linux kernel, at least in recent incarnations, supports so-called automatic page migration. You can look it up. You can determine whether or not it's enabled on your system by printing the contents of /proxys kernel NUMA balancing If this gives you 0, NUMA balancing is off. If this gives you 1, it's activated. If you have super user privileges, you can actually echo a 1 into the file to activate it. Now what it does is it monitors for every process the locality properties of memory access. Let's not dwell on how this is actually done. So it tries to monitor whether you have a lot of non-local accesses to certain memory pages, and when this happens on a memory page, it tries to move the page into the memory domain of the thread that accesses it most frequently. There are parameters on Linux that control the aggressiveness of this process. It's entirely clear that this automatic page migration feature cannot be too aggressive. If it's made too aggressive, then the machine could end up in a state where it does nothing but move around memory pages. This has to be prevented. So here, if you look into the contents of Proxys kernel, then there's a couple of files starting with NUMA balancing, and you can play with these parameters, but you need to know what you're doing to not have hazardous impact on the performance of the system. So the default behavior is to take it slow. If you have a program that allocates huge amounts of memory and operates on this memory for a long time, and a long time means tens of seconds or minutes at least, then the NUMA problem is automatically healed. So it takes some time to kick in, but as soon as you're iterating over the same memory space again and again, it will heal the NUMA problem. However, do not rely on it. There's no guarantee that on a particular system you're on, this NUMA balancing feature is actually available. So it might be turned off for other reasons you don't have influence on. So parallel first touch in an OpenMP program is still a good idea whenever there's a chance that your team of threads spans multiple NUMA domains. Alright, so here's a summary on ccNUMA. First of all, identify the problem. Is there a ccNUMA issue in your code? There are different possibilities. A simple test is to run with NUMA control --interleave. Of course, if there's a problem only in part of your code, then NUMA control --interleave might just make it worse. So that's not a safe thing, but you might give it a try. Apply first touch placement. Look at the code where your data is initialized and parallelize these loops using static scheduling, and use the same scheduling for loops that later access that data. C++ and global or static objects may require special care. There are specialized solutions for that, and that can be, the problem can be mitigated. NUMA balancing or automatic page migration is active on many Linux systems today. It's a slow process, so it may take many seconds, but not a general solution. So it's always good to have parallel first touch in mind, even though you know that you're on a system where NUMA balancing is active. And finally, if you have a program that needs dynamic scheduling because you have load balancing problems, then it's still a good idea to do parallel first touch. So if there's anything you take home from this part of the lecture, if you do OpenMP, do parallel first touch. In the second part of the lecture, I'd like to show you a little case study about the parallelization of a Gauss-Seidel solver. It's one of the examples where, looking on it, you think this can never be parallelized, but in fact it can. So what is it about? We're dealing with a 3D matrix-free Gauss-Seidel smoother. You might know the Gauss-Seidel algorithm from a numerics lecture or math lecture. It is an iterative solver for a linear system of equations, ax equals b. You solve it iteratively by computing a new approximation xk from an old approximation xk of xk minus 1 by using the entries of the coefficient matrix A in a peculiar way. So whenever you compute a new component of the result xi, you immediately use it the next step in the computation of the next xi plus 1. So this is why the Gauss-Seidel solver doesn't appear to be parallelizable right away, because every step of the process depends on the result of a previous step. In this particular example here, we use this Gauss-Seidel algorithm for solving a partial differential equations, Laplace equation, Laplace x equals 0, and we use Dirichlet boundary conditions. So we're solving a PDE as a boundary value problem. So here's the core of the algorithm. We have an outer loop of iterations. In this simple benchmark, we set the number of iterations to a fixed value, IT max. Of course, in reality, would employ some kind of convergence check to stop the calculation whenever a given convergence criterion is met. But that's not the issue here, so we just set a fixed number of iterations. And then we have a 3D problem. So we have a three-way loop nest over k, j, and I, all going from 1 to a maximum value -1. And in the inner loop iteration, we update x of kji with a sum of the 6 neighboring values, so x kji -1, x kji +1, and so on. We sum them all up, divide by 6, and that's our new value. These kind of algorithms are also called relaxation algorithms, but in fact, if you know your numerics, this is just a sparse matrix vector multiplication in disguise. So we use it typically on sparse problems, as is this PDE problem with the Laplace equation. Now what happens when one particular element x of kji on the left-hand side is updated? So let's look at this like a snapshot in time. So we're updating this particular element kji, and these 6 neighbors can be grouped into distinctive groups. We have new data and we have old data. New data means that in one of the previous iterations over k, j, or I, this data has already been updated. So in this formula, this is something that carries the index k, which is from the current time step of the current approximation. If we look at a geometric representation of these neighbors, it means that if these are our Cartesian axes, I, j, and k, then these brown neighbors, denoted also in brown in the code here, these have been updated within the same sweep, so within the same time step. While the blue neighbors are old data, which means this is data that will be updated in this sweep, but hasn't been updated yet. So that's why we call it old. It's from the previous approximation that carries the index k-1 in the formula. So one half of the 6 neighbors is new data, and the other half is old data. And of course, we have a problem here because the new data has just been updated, depending on which coordinate we look at. So for example, x of kji -1 has been updated in the previous I iteration, so just before we update kji. And this is of course a problem with parallelization. This is why just writing naively an OMP parallel 4 in front of the k loop, or any loop for that matter, will not work, because we have loop carried dependencies on all spatial loop levels. X of kji is computed using x of kji -1, x of kj -1i, and x of k -1ji. Each of these 3 neighbors has been computed in the previous I, j, or k iteration. So whatever you do, whichever loop you would choose for parallelization, it will not work because you have a loop carried dependency. The central question is, can we solve the problem still in parallel, but keep these dependencies intact? Now, the nice thing about these iterative algorithms is that even if you do it wrong, even if you just write pragma OMP parallel 4 in front of the for loop, you would still get a converged result. But it's not the result you want. It's not the algorithm you want, because you violate the algorithmic conditions, so these dependencies, which we need for implementing the correct algorithms. Of course, there are multiple ways of rewriting this algorithm in different ways, or modifying it to make it more accessible to parallelization. But here, in this particular case, we want to parallelize it as it is, without modifying it. We want, if you want, a bitwise identical solution to the serial execution. So how do we do that? The idea that we employ here is called wavefront parallelization. Now, usually if you parallelize something with multiple loop levels with OpenMP, you choose the out loop, which would be the K loop in our case. However, in this Wavefront approach, the actual parallel loop is the J loop. So we chop the J loop into chunks, and there are as many chunks as there are threads running in the problem. The outer dimension K is not the OpenMP parallel dimension. It's actually a sequential dimension. It is the dimension in which the Wavefront scheme works. The inner dimension I is always traversed completely. So whichever thread gets a particular KJ combination always traverses, always updates the complete range of I's. Now if we look at this picture, then we subdivide the problem into blocks. Each block has a height of 1 in K direction. It has a width of whatever the complete width of J is, divided by number of threads in the J direction, and it has a depth of I max in the I direction. If you look at a block like this one, then you see immediately that this block can be updated if its dependencies are met, which means that if the left and the bottom block, as seen from this current block, have already been updated. So, as opposed to first impressions, we do have a lot of parallelism in this problem. We just have to adhere to these dependencies. A block can only be updated if its left neighbor and bottom neighbor blocks have already been updated. Apart from that, we can do whatever we want. So this means that all the blocks that are on one of these red dashed lines can be updated in parallel. Whenever the blocks in the W2 line have been updated, I can synchronize the threads that have been doing that, and then I can update the 3 blocks in the W3 line in parallel. So as this wavefront progresses, I can keep more and more threads busy by putting more and more blocks to the threads. Of course, in order to make this work correctly, after each wavefront, after each update of parallel blocks, we have to synchronize the threads working on them in order to get correct ordering of the events. Now this means in the beginning, the number of threads that have something to do is small. Actually, right at the beginning, where only one block exists that has its dependencies fulfilled because it's a boundary block, right at the beginning, only one thread can work. This single thread works on this single wavefront, W1, which comprises only a single block. After this block is finished, we can keep 2 threads busy and so on. So there's a wind-up phase where not all threads are active. So this wind-up phase goes on until the complete range of J is actually covered. And since we chopped the J range into as many blocks as there are threads, this means the wind-up phase takes as many steps as there are threads. This is a picture of the fully developed pipeline phase. All threads are active. So thread number 0 gets the first block, thread number 1 gets the second block, 1 coordinate down in K, thread number 2 gets the third block, and so on. And all threads are active. Now, of course, when the computation, when the sweep nears its end, this is when the thread number 0 hits the top of this box. Then the wind down phase starts. You see why this has a similarity to pipelining, and it's actually also called pipeline parallel processing. Now, after T0 has completed its complete K loop, it goes idle, and only T1 to TT are busy, and then the wind down phase starts, and fewer threads are busy till in the end the right top block is being updated by the last thread, and then the computation is done. So this seems simple enough as a scheme, but of course it's evident that in terms of OpenMP, this is not so easy to implement. So you have to think a little bit. And here's a solution to that, and I hope I can make it clear to you. Now, of course, we cannot just employ simple loop work sharing. This doesn't work. We have to do the work sharing manually, starting with the fact that we need to chop the J loop, the middle loop, in equal chunks. So this is done here. We open a parallel region. We compute the number of threads and the thread ID for every thread. which are private variables, we compute the start and the end index in the j direction. So this has to be done manually here because we don't have the facilities of a parallel loop at hand. The time-stepping loop or the iteration loop is still on the outside. We're doing the k loop here, and interestingly, the k loop doesn't go from 1 to k max. It goes further than that. In order to compensate for that, we mask out certain parts of the k loop. So with this if condition and the computation of kk equals k minus tid here, we make sure that the wind up and wind down phases are done correctly. The first thread starts right away computing, while the other n-1 threads have to wait for some time until the winding up pipeline hits them, and then they can participate in the computation. The inner loop iteration looks very similar to the original code, apart from the difference that we now write kk instead of k. Kk is different for every thread, because every thread works on a different layer in the k direction. Now, there's one thing missing still. We need to synchronize the thread after every Wavefront update, which is after every increment of the k variable, and this is done by this implicit OMP barrier down here. So this is one of the cases where you need an explicit OMP barrier in your code. This is the code for Wavefront parallelization or pipeline parallel processing of a Gauss-Seidel smoother in OpenMP in 3D. Of course, there are some open questions here. We know global barriers are expensive, so is there probably a way to remove or mitigate this cost for the global barrier? Because usually if we do a complete sweep over some domain, we have an implicit barrier at the end. This is just how OpenMP does things. In this case, we have k max minus 2 global barriers. So the overall barrier overhead is much higher here than if we only had done like a Jacobi sweep where everything is nicely parallel without any dependencies. Can we find a remedy for that? Interesting question. Also, is there a global performance limit? The minimum data traffic that we have to account for is that we have to update the whole array exactly once. Of course, there's some problems here because there's a neighboring access, x of I minus 1, x of I plus 1, and we're not really sure whether these are cache hits or not, but the absolute minimum data traffic that has to be there is reading and writing the whole array exactly once. So the minimum traffic is read and write Imax times Jmax times Kmax elements. And this means since each element is 8 bytes, 16 bytes per lattice update. And we could try to validate this hypothesis using a measurement, for example. Should simultaneous multithreading give better performance? Of course, there's a dependency. So the iteration I of the inner loop depends on a result that has been computed in iteration I minus 1. So there is a dependency between loop iterations, between successive loop iterations. And this means we have pipeline bubbles. Pipeline bubbles means simultaneous multithreading where multiple threads run on the same physical core could have some benefit. There is a dependency after all, so we should give it a try. And finally, how about ccNUMA? So this parallelization scheme using a parallel loop over the middle dimension of the grid is very nice, very ingenious, but it might run against ccNUMA placement. And is this an issue here? Important questions to answer, because in such kinds of solvers we often deal with large problems, a lot of memory, which means the problem is after all memory bound. So NUMA has to be taken into account. Thank you.